Welcome to the video on organometallic compounds. This video will show us one of the very common ways to make carbon-carbon bonds. Organometallic compounds are when we have a carbon group next to something that is electropositive. And so here we have lithium and magnesium and copper as three possible examples. So this is called an organolithium compound, an organomagnesium compound, or an organocopper compound. And in each case, our metal, the lithium, the magnesium, and the copper, are positively charged, and our carbon then is becoming negatively charged. And so this allows us to have carbon act as a nucleophile. So because carbon is more electronegative than the metal that it's bonded to, it will have the partial negative charge. And shown down here are some electronegativity values from the periodic table. So if we're thinking about putting those metals next to carbon, the differences in their electronegativities cause that partial charge to happen. And so when we have lithium and magnesium, our carbon is going to be very reactive because the difference between the two is greater than if, say, we have copper, which is a little bit closer in the value. These are all metals used in organometallics, but these are the two that really stand out and make our carbon very negative. Some properties of organometallic compounds. So if we take those two very common metals, lithium and magnesium, and we make them into organometallics, it will be called an organolithium compound and an organomagnesium compound. And so we can imagine the lithium attached to the carbon. Again, this is going to be partial positive and this is going to be partial negative. Actually, because the difference is great enough, we can think about it like this, where our carbon has a full out negative and our lithium is full out positive. And same with our magnesium compounds. As we get further into the chapter, I will explain how we make our organolithium compounds and our organomagnesium compounds. This carbon is partial negative and this magnesium is partial positive. And so we can also think about it as a full out negative and a full out positive. And so the cool part about that is in both of these cases, that carbon group can act as a nucleophile. Okay, if we concentrate on organolithium compounds to start, if we start with an alkyl halide and react it with two equivalents of lithium, we end up replacing the halogen with the lithium. So we have the carbon group next to our metal like we want, our other lithium hanging out with the halogen that was originally attached to our carbon. And so we see that in all cases. So here we have a primary alkyl halide and we get a primary organolithium. Here we have our halogen on a benzene ring and then our lithium comes on our benzene ring. So that makes that carbon right there partial negative. So that acts as a nucleophile. That looks a little different than anything we've seen before. And finally, we can have our halogen right on a double bond, which will give our lithium right on a double bond. And then ultimately, the carbon that is partial negative or full out negative is going to be the carbon on the double bond. Now, if we switch gears and talk about our organomagnesium compounds, and these are specifically called Grignard reactions. And so what happens is we start with an alkyl halide, just like the organolithium, and we add magnesium metal in the presence of ether, and we end up having that magnesium insert itself right in between our organo piece and our halogen. And so we end up with this RMGX. This species right here should start to become very familiar to you. Our magnesium is going to be partial positive and our carbon is going to be partial negative, if not full out positive and negative. And the halogen just hangs out and supports that magnesium. We can do primary, we can do on the benzene ring, and we can do on a double bond. This looks very similar to what we saw with the organolithiums. So the mechanisms that we use to form organolithium and organomagnesiums are free radical mechanisms. So we will not be required to know the mechanism for the formation of a Grignard or an organolithium compound. For the Grignard reagent, we need diethyl ether or THF as the solvent. And so we have our alkyl halide with our magnesium and ether, and then we end up getting our Grignard reagent right here that's then also partially stabilized by these ether molecules. So organomagnesium, Grignard reactions, and organolithiums, both are very strong bases. So as a base, they're going to react with anything that's protic. So water and alcohols, so anything that has a proton that can be donated. What happens is we have this very great nucleophile, this full out negative charge on our carbon, which is also a very strong base. And so that is going to be easily protonated reacted by anything that has a proton. Remember, we can compare the pKa's to figure out which ones will work, but considering this is our weakest acid, it's pretty likely that most protons that are transferable will in fact quench this Grignard reagent. Once we protonate that Grignard reagent to make our alkane, then we no longer have a reactive species. We no longer have a nucleophile. This is a bad thing. So very often our Grignard reactions and or reagents need to be away from water or alcohol or any moisture. So if you have a compound that has an alcohol and an alkyl halide in it, we will not be able to use Grignard because the OH will quench once that Grignard is formed. And the word quench here, I just mean ruin it. It'll make it so that it's not a negative carbon anymore. So some places that we can actually use our Grignard reagents, we can use it with an aldehyde or ketone, that negative carbon will react right at the carbonyl to get us from a ketone or aldehyde to an alcohol. We can use our negative carbon to react with an epoxide to kick open that ring. We can use our Grignard reaction to react with CO2, and that will give us our carboxylic acid. We can use that Grignard reaction to react with an ester, and we need two equivalents, and it'll actually happen twice to bring us to our alcohol. And we can have our Grignard react with a nitrile to give us our ketone or aldehyde. So now moving forward, we'll talk about Gilman. And the Gilman reagents contain a lithium dialkyl cuprate. And so what happens here is we start with our organohalide again. We have two equivalents of lithium. And just like before, that one lithium takes the halogen. And so we end up with an organolithium, negative carbon, positive lithium. Then we subsequently react that with this copper halogen here. And what happens is we lose another LIX, and we have our copper in the middle sandwiched by two R groups, and then our lithium hangs out as a cation next to this anionic species right here. And this right here, this dialkyl cuprate with the lithium hanging out, is our Gilman reagent. And so Gilman can react with alkyl, vinyl, or aryl. So we can have primary on a benzene on a double bond. And so what happens is we end up attaching two of those groups on. And so this is our reactive species, and we have this carbon is the one that's reactive, the one right next to the copper, and that is going to be the species that acts nucleophilic. Only one of them will react though, not both. So some reactions that we have, if we have this Gilman reagent here, this dialkyl cuprate, our negative R is going to attack the carbonyl right there and replace that chlorine. We'll talk about that acyl substitution in the next chapter. We can have our negative R attack the beta position, and we'll learn about that next semester. But we can see that these dialkyl cuprates with lithium hanging out, the Gilman reagents, can be used nicely as a nucleophile as well. We can also use this negatively charged carbon as a normal nucleophile in an SN2 type reaction where we have a halogen link. And so this is called coupling. And so Gilman can also couple with an alkyl halide in an SN2 type reaction, and we end up with a new carbon-carbon bond, which is pretty exciting. Another way that we can use these Gilman reagents is with a primary, an aryl, and a vinyl alkyl halide, replacing one of our R groups. And so we see that substitution. This reaction will not work on tertiary and most secondary alkyl halide because we have a competing reaction that's called elimination, which we actually haven't learned about yet. That comes in organic too. More about Gilman. This coupling reaction allows us to make a carbon-carbon bond from two organohalides. We start with RX and we create the Gilman out of that. Then we use R prime X to couple, and then we end up coupling those two carbons together, which is a very important reaction, being able to make that carbon-carbon bond. We can't forget Simmons-Smith reactions and carbenoids. What I want you to take home from this is we can start with an alkyl halide, and we can use zinc in ether, and that is going to create this species right here. And although that carbon zinc bond right here is not crazy polar like the carbon magnesium bond, we do get a nice partial negative here, and so that will react as a nucleophile. So zinc works as well. So if we quickly review, we can have organolithium acting by itself as just a simple organolithium compound, having that R group act as a nucleophile. We can have magnesium to make a Grignard reagent here, where that carbon right there is negative and acts as a nucleophile. We can have the Gilman reagents, where we use 2 R groups to make that a nucleophile that we can use in a subsequent reaction. And then we can use this Gilman reagent to couple. So we have the Gilman produced from 1 alkyl halide shown here, and then we have a second alkyl halide, and then we can actually make this new carbon-carbon bond, which is pretty cool. Have fun making new carbon-carbon bonds.